The first law of thermodynamics, examples part 2. Consider the following problem, example number 3. You have a series of thermodynamic processes as provided in the PV diagram shown. In the PV diagram, you have state A, state B, state C, and state D. State A, the volume of the system is 2 times 10 to the negative 3 power cubic meter, and pressure is 3 times 10 to the 4th power Pascal. State B, the volume is also 2 times 10 to the negative 3 power cubic meter, but the pressure is 8 times 10 to the 4th power Pascal. State C, the volume of the system is 5 times 10 to the negative 3 cubic meter. The pressure is 3 times 10 to the 4th power Pascal. And finally, state D, the pressure is 8 times 10 to the 4th power Pascals, and the volume of the system is 5 times 10 to the negative 3 power cubic meter. The problem tells us that in process AB, from state A to state B, 150 joules of heat is added to the system. Whereas in process BD, from state B to state D, 600 joules of heat is added. Determine the total heat added in process ACD. So ACD, what is the total heat added? So here we see two paths, process AB, then BD. You have path ABD, and then you have process ACD, so path ACD. So you have path ABD and path ACD. In both instances, in both paths, you have the same initial state and final state. So initial state A, initial state D. So as mentioned in the problem, the given is QAB is 150 joules, QBD is 600 joules. The pressure at A is the same as the pressure at state C, 3 times 10 to the 4th power Pascal. Pressure at state B is the same as pressure at state D, 8 times 10 to the 4th power Pascals. And the volume at state A and B are the same, 2 times 10 to the negative 3 power cubic meter. And the volume at state C and state D are equal at 5 times 10 to the negative 3 cubic meter. Now, the change in the internal energy of a system does not depend on the path taken by the system. What's important is initial state and final state. As we had mentioned, path ABD and path ACD have the same initial state and final state. So that means they have the same change in internal energy. Delta U is just equal to delta U ABD is equal to delta U ACD. Let's take a look first at delta U ABD because we know QAB and QBD. Delta U ABD is just equal to QABD minus WABD. QABD is the heat added as you go from A to B to D. So QABD is just equal to QAB plus QBD. We know QAB 150 joules, we know QBD 600 joules, so we are able to get QABD 750 joules. Similarly, work ABD WABD is just equal to WAB plus WBD. Going back to the PV diagram, ABD, from A to B, the volume is constant. Since the volume is constant, that means zero work done. So, WAB is 0. Whereas, from B to D, the volume changes and the pressure is constant. That means the work done at path BD, the work done from B to D, is just equal to pressure at state B, PB, times the change in volume, VD minus VB. Knowing that we know PB and we know VD as well as VB, we are able to calculate WABD to be 240 joules, which means we are now able to get delta UABD. QABD 750 minus WABD 240. 750 minus 240 will give you 510 joules. So delta UABD is 510 joules. That means delta UACD is also 510 joules. And delta UACD is equal to QACD minus WACD. Transferring WACD to the other side, QACD is just equal to 510 plus WACD. So to get the final answer QACD, all we need to do is find WACD. And WACD is just equal to WAC plus WCD. So again, going back to the PV diagram, ACD, the work done from A to C, the volume changes at constant pressure. So that means WAC is just equal to pressure PA times change in volume VC minus VA. Whereas the work done from C to D, the volume is constant. That means the work done is 0. So WCD is equal to 0. Knowing PA, knowing VC, and knowing VA, we are able to calculate WACD to be 90 joules. QACD is 510 plus WACD. So QACD is 510 plus 90. QACD is just equal to 600 joules. The heat added as you go from initial state A to final state D along the path ACD is 600 joules. Next, we have the following example. Example 4. You have 1 gram of water which has a volume of 1 cubic centimeter. It becomes 1,671 cubic centimeters of steam. So from liquid, it became gas to steam when it is boiled at a constant pressure of 1 atmosphere. 1 atmosphere is equivalent to 1.013 times 10 to the 5th power Pascal. Using heat of fusion, heat of vaporization rather, L sub V equal to 2.256 times 10 to the 6th power joules per kilogram, determine the increase in the internal energy of the system. It doesn't matter if it's 1 cubic centimeter of water or 1,671 cubic centimeter of steam. The mass remains to be the same, 1 gram. So correction, this is not stream, this is steam. Okay? So from water to steam, the mass remains the same, 1 gram or 0.001 kilograms. The volume changes from 1 cubic centimeter to 1,671 cubic centimeter, convert to cubic meters. The pressure is constant at 1 atmosphere or 1.013 times 10 to the fifth power Pascal. And we are given the heat of vaporization of water. The change in the internal energy of the system is just given by delta U is equal to Q minus W. Now, Q is the heat added to vaporize the 1 gram of water. So from our calorimetry, phase change from liquid to gas, Q is just equal to mLV. Work for constant pressure from initial volume to final volume is just P times V2 minus V1. We know M, LV, P, V2, and V1, so the equation is complete. We are able to calculate the change in the internal energy of the system to be 2087 joules. And with that, we are done with the first law of thermodynamics. In the next video, we will move on to the second law of thermodynamics. Thank you for watching.